Hi, now we can talk about dot product between vectors. Dot product will turn two vectors into a scalar. If you don't know what is a scalar, it's just a number. Instead of vector, they are just a number. And the main idea of dot product is to measure a vector with respect to another vector, but also multiply by their length. The way we measure is by projecting one vector to another. And that is the dot product definition. So we have vector v dot vector u is equal to the length of v multiplied by cosine theta and multiplied by the length of u. And one thing to remark is that this length, the projection, we project v onto u, is actually equal to the length of v and cosine theta. So this and this together is the length. It's the length of the projected on vector u. As before, we like to express our vectors into a basis vector, which is the common vector we will use to express most another vectors. So since we are working 2D, in 2D we have E1 is which is a vector pointing right, and E2, a vector E2 is pointing up. And one thing to notice that we also choose them such that E1, the vector E1 is equal to 1. Also the vector also is same with the vector E2. Yeah, they are all equal to 1. And we also choose them such that E1 are 90 degrees with E2. Which actually, if we use the definition of dot product, we mean that E1 dot E2 is equal to 0. Is equal to cosine 90 degrees, which is equal to 0. And let's say if v is equal to v1, the vector v is equal to v1, which, you know, v1 is just a scalar. E1 plus v2 vector E2, and we have vector u equal to u1 E1 plus vector u u2 E2. If v1 v dot u, it will be v1 E1 plus v2 E2 and dot u1 E1 plus u2 E2, and it will become v1 v1. Oh, okay, I think I just write it here. It'll be v1 u1 E1 dot E1 plus I think I need to move them a little bit below. Yes. And plus v1 u2 E1 dot E2 plus v2 v2 u1 equal to E2 dot E1 and plus u2, no, sorry, v2 u2 e1 no e2 dot e2. And if you look at the definition here, you look at if you look at the definition here, we can clearly see that v dot u is equal to u dot v, right? So because switching this order, the scalar switching switching order of scalar, and the product will be the same, right? It's just normal product between scalars. So e1 dot e2 and e2 dot e1 will be the same. And we also know that the e1 dot e2, since they're 90 degrees, they are 0. So these are 0, 0, right? So what and that doesn't matter because you multiply something multiplied by 0 is 0. So what we end up with is just e1. Oh, sorry, here's also 1. v1 u1 plus v2 u2. And one thing to notice is that we have a 2 vector. So I think I use another color. No, just still using orange. So these two guys are vector. These are vector. These are also vector. And what we end up with is scalar. So yeah. So we turn 2 vector to a scalar. So if we want to measure v, only the projection of v to some particular direction, so you can do v dot w. Let's say that it's a particular direction, but you want to divide it by the length of that arrow, such that this vector have a unit length. Then you are only measure the projection. Otherwise, you will multiply by its length. So this is how we measure. Using a vector. How we measure between vector. And another thing is that keep in mind, since vector can, as we said before, vector space, it can be different object. The idea behind is that we can only using a similar object to measure another similar object. So we are using an arrow to measure another arrow. And those objects are not necessarily number. Just like in our case, our object is arrow, and they are not number. So in order for us to measure another arrow, we need to using another similar object, which is also arrow. We have looked at the dot product in 2 dimensions. Now let's look at the dot product in 3 dimensions. Just like 2 dimensions, in 2 dimensions we're using 2 bases to express every another vectors. In 3 dimensions, we are going to use three basics vector to express any another vector like v and u. Yeah, and we choose these 3 basics vector. These 3 basics vector like before, like everybody, every basics vector have length 1. And the dot product between the same two basis vector, the dot product between 2 basis vector is 1, and the dot product between 2 basis vector that are different is equal to 0. And then we can express every vector into these 3 basics vectors. And the dot product just like before, and it will turn two vectors two vector into a scalar. One thing worth to mention about the terminology: when the dot product between two different basis vector, like this EI and this EJ, is equal to 0, when it is equal to 0, we call the relations orthogonal because they are 90 degrees to each other. And when we choose the basis vector that it has length 1, such that you can think about this vector is normalized because it has length 1. We will also say that it's normal. And together with this condition, orthogonal and normal, we will call the basis orthonormal. And this is the most common basis people use, because now we generalize the dot product in any n dimension. So n can be 1, 2, 3, 4, 5, 6, 7, 8, and n can be any positive integer you want. So we just like the same idea before. We will have orthonormal basis, and this is just all the basis vector has length 1 if a dot product with itself is 1, and dot product with other basis vector is always 0, and we can write it in a summation form. Write every vector with respect to the basis vector in a summation form. So we will sum this the dummy index I from 1 to n. And this symbol imply the summation, and this same thing for the vector u here. Oh, sorry. And then we apply the dot product, and just like before, if you remember the definition, and since we are expressing everything with the orthonormal basis, we will just get a scalar here. So one thing to notice that v vector is a vector, u vector is also a vector, and the dot product between them is a scalar. They are no longer vector. So yeah, they are no longer vector.